So today we'll talk about dimension preserving reductions between SVP and CVP in different p-norms. And this is joint work with Divesh Aggarwal, Yanlin Chen, Zeyong Li, and Noah Stephens-Davidowitz. So as you can see in the title, there are two keywords. One is dimension preserving reductions, and the other one is SVP and CVP. So let's try to see what these keywords mean in this talk. So first we'll talk about what reductions we are interested in. So when we see a polynomial time reductions, so most of the time we use them to show the NP hardness of the problem. And one of the consequences in polynomial time reduction, the problem size also increases by a polynomial factor. And sometimes this polynomial factor might be too big. And if we want a fine-grained hardness result by using this polynomial time reduction, then the problem size increment will not be good for us. We want to make sure that the problem size will not increase by much. And so that's why we move to exponential time reductions. And these reductions are good only if we believe that the problem is exponentially hard. And in this case, if we are able to find a reduction in which the problem size does not increase much, then it implies a fine-grained hardness. So let's see this through an example. So let's see, we have two problems, A and B. And for problem A, we know a lower bound T. And if we can have a reduction from A to B, which takes time T prime, where T prime is significantly less than T, then the fine-grained hardness of B is almost as the fine-grained hardness of problem A. So we don't want that if T is exponential, then we are fine something just smaller than T prime, which is smaller than the T in the constant in the exponent. So that's fine for us. We don't want that the T prime should be polynomial or even something smaller than that. So even exponential is fine for us. And because we are moving from polynomial time reductions to exponential time reduction, it is also possible that we can also control the problem size. So this is the motivation for us to study the exponential time reductions. And the next keyword in the title was SVP and CVP. So why we study SVP and CVP is these problems are conjectured to be secure even after quantum computers. And the lattice-based cryptosystems, security can also be based on worst case hardness of the lattice problems. So this is a unique property which is known only through lattices. And there are many powerful crypto primitives whose construction is known only through lattices. And one of the popular example is fully homomorphic encryption. And because of all these properties, lattice-based cryptosystems is the most popular candidate for post-quantum crypto. So the post-quantum crypto means that the classical crypto systems which are secure even after quantum computers. So this is the motivation for us to study SVP and CVP. And in this one, we will talk about the reductions between SVP and CVP in different LPNorms. So let's discuss what exactly the lattice is. So a lattice, L, is a discrete set of points in a real space. As you can see, this is a two-dimensional lattice. A lattice is generated by a basis vectors. A basis is a set of linearly independent vectors, such that if you take all the integer linear combinations, you will get all the lattice. You will generate all the lattice points. So in this one, the basis is B1 and B2. So in this talk, I will use n to denote the rank of the lattice, where rank means the number of vectors in a basis, and we'll use m to denote the dimension, where dimension of the lattice is same as the associated dimension of the real space. So before talking about the lattice problems, SVP and CVP, let's first define some of the notations which I'll use in this talk. The first one is LPNorm, and we are more familiar with the Euclidean norm, but in this one we'll study all the LPNorms. So for a finite p, it is just take the pth power of each coordinate and then sum it up, and then take 1 by pth power of the sum. and infinity norm is just the max of all the coordinates. So this is LP norm, and the notation is lambda 1. So lambda 1 represents the uh, length of the shortest non-zero vector in LP norm. So we'll use lambda 1 to denote this quantity. And the distance so for any lattice and the target vector t, the distance between t and L is the minimum distance between any lattice point and the target vector t. And the last notation is LP ball. So to represent a LP ball of radius r, we will use the notation r times b subscript p to the m, which says that it contains all the points which has LP norm less than equal to r. So in this one, the red ball is of radius lambda 1 and the orange ball is of radius 2 lambda 1. So now we are good to define the shortest vector problem. So in the shortest vector problem, we are given a basis, and for the gamma approximation of the shortest vector problem, we have to find a lattice vector such that first of all it should be non-zero vector, and the LP norm of the vector should be at most gamma times lambda 1. So in this example, if you find any vector within the red ball, any non-zero vector within the red ball, you solve exact shortest vector problem. If you find any vector in orange ball, you solve two approximation of shortest vector problem. And the next problem is closest vector problem. So in this one, we are given a basis and also a target vector t. And the problem here is to find a lattice vector v such that the distance between v and t in LP norm is at most gamma times the minimum distance in LP norm. So in this one, if you find any lattice point within red circle, you are solving exact CVP, and in orange circle, you solve two approximation of CVP. So these are the class of problem which we'll be interested in, SVP and CVP in all the different LP norms. So now let's first see what we know about these problems in terms of approximation. So we know that at least m to the power 1 by log m approximation of SVP and CVP in different LP norm is hard. And we know that square root m approximation or square root m by log m approximation is not NP hard. If it becomes NP hard, then the polynomial hierarchy collapses. And with respect to cryptography, the interesting reason of approximation is polynomial approximation factor. So all the crypto systems which we know right now are based on either small polynomial approximation like m square or m to the power 1.5 polynomial m to the power 5 approximation of SVP and CVP. And in terms of polynomial time algorithm, the best approximation factor which we can achieve till now is 2 to the power m log m by log m, which is almost exponential. So this is the best approximation factor which we get in polynomial time. So this is all we know with respect to the approximation factor. So now let's talk about the algorithms for SVP and CVP. So most of the study for algorithms is for SVP in L2 norm. So we know that any approximation of SVP can be done in 2 to the constant times 2 to the power c times m, where c is a constant which depends on the approximation factor, and we also know that the c is less than equal to 1. And for CVP in different p norms, we only know that it takes exponential time, and also for SVP in different in SVP when p is not equal to 2, we also know that this is exponential time. But the point to note here is when p is not equal to 2, we don't have any bound on the constant c. We have not well studied the constant c in the exponent. So there is no good upper bound known for CVP and SVP in P not equal to 2. So in terms of lower bound, recently there is a series of work in which Aggarwal, Bennett, Golovne, and Stephens-Davidowitz show that CVP P and SVP infinity, for a small constant approximation, there is a lower bound of 2 to the power 1 minus epsilon times n. And to show this lower bound, they assume gap strong exponential time hypothesis. So this is all we know about algorithms, and it is very unfortunate that we are not aware about any good upper bound when p is not equal to 2. So in this work, we'll try to give some upper bound when we look at a constant approximation of these problems. So now let's talk about what we know in polynomial time reductions. So when we look at the reduction between CVP and SVP in the P norm, like we preserve the norm, we know a efficient reduction which preserves the approximation factor, which preserves the dimension and the rank. But in other direction, the reduction is only known from between L2 norm, and in this one we lose at least square root m approximation factor. So the reduction is from gamma square times square root m approximation of CVP in L2 norm to gamma approximation of SVP in L2 norm. So these are the only two reductions which we know, polynomial time reductions which we know from between CVP and SVP. And now let's talk about reduction between CVP and CVP and SVP and SVP in different LP norms. So one of the trivial way of getting a reduction is by using the norm inequalities. And we can show that there is a reduction from SVP P to SVP Q, and which increases the approximation factor by m to the power 1 by P minus 1 by Q. And there was nothing much known till Regev and Rajendra came up with a norm embedding idea and show that C times gamma approximation of SVP in L2 norm reduces to gamma approximation of SVP in LP norm. And here C is a constant. But this reduction has a drawback that there is a super constant increment in the dimension, at least when P is greater than equal to 2, and P is greater than 2. And this reduction only holds from L2 norm to LP norm. So if we are interested in dimension preserving reduction, then this reduction is not good for us. So this is all known about polynomial time reductions between CVP and SVP. So now let's talk about exponential time reductions. So in this direction, the first reduction came in 2002 when Kumar, Shiva Kumar gave a exponential time reduction from constant approximation of CVP to a variant of SVP, which is almost uniformly sampling the lattice vectors within a sphere of bounded length. So this reduction takes exponential time, and there is no bound known on the constant in the exponent. And later this reduction is generalized to all LP norms. And then recently Eisenbrand and Engine gave a algorithm for constant approximation of SVP and CVP in different LP norms by using the current fastest algorithm for SVP in L2 norm as a subroutine. And the only drawback of this reduction is it uses some specific properties of the current fastest algorithm. So this is not a general algorithm which can work with any SVP2 oracle. So this is all known about exponential time reductions between SVP and CVP. Now let's talk about our contribution. So in this work, we gave a series of reductions. And so let's first take that P and Q is between 1 and infinity, and P is less than or equal to Q. And we gave 2 to the epsilon m time reductions. First is from SVP Q to SVP P, means SVP in a higher norm to SVP in a smaller norm. And then the similar reduction for CVP, but now we are reducing from P norm, LP norm to LQ. So we are reducing from a smaller norm to a higher norm. And the last reduction is from CVP to SVP, which is from CVPQ to SVPP. So in these reductions, the loss in approximation factor is in the first reduction is 1 by epsilon to the power 1 by p, and in the last reduction it's slightly higher, it's 1 by epsilon to the power 1 plus 1 by p. And if you see the reduction 3, then we can also get a reduction like CVPP to SVPQ just by using reduction 1 and 2. So let's see this. So first, all these reductions has a one very special property, which is like they either preserves the dimension or rank or increase them by at most 1. So these reductions are really good for us to study the fine-grained hardness of the lattice problems. And we also know that these problems are at least, or we believe that these problems are at least exponentially hard. And now we have a efficient reduction which preserves the problem size. So these reductions are good for us to study the fine-grained hardness of these problems. So this is a pictorial view of our result. So the dotted line represents the already known results by Michan from 99, and the solid line represents the reduction in this work. So we also have one more contribution, which is when we are interested in LP norm when p is between 1 to 2. In this case, we get a better reduction from CVP to SVP in LP norm, and the loss in approximation factor here is order of 1 by epsilon to the power 1 by p, which is at least smaller than 1 by epsilon factor, which we had in the last reductions. And one of the consequences of this result is when we plug in p equal to 2 and epsilon equal to log m by m, we get a polynomial time reduction from square root m by log m approximation of CVP2 to SVP2. And this is a improvement on Cannon's celebrated polynomial time reduction from square root m approximation of CVP to SVP. So these are all our contributions. So now let's talk about the reduction ideas. So I will focus on one of the reduction from CVP to SVP, from larger norm to a smaller norm. So the main idea here is Condensed embedding, which is already known. And let's first talk about what is Condensed embedding. So in this one, we are given a SVP oracle and we want to solve a CVP problem. And the idea here is first generate a lattice B prime, where B is the basis of the original lattice, T is the target vector, and S is a constant which we'll choose very carefully. And we know that a short lattice vector of basis B prime is of form V plus K times T, and the last coordinate is K times S, where K is an integer. And if we want to get a CVP solution by using SVP oracle, we have to force the algorithm to output a solution with K equal to 1. And recently, when Eisenbrand and Wengin, they observed that it suffices to simultaneously find two lattice vectors which are close to K times T, and the other one is close to K minus 1 times T. So if we have these two vectors, and if we try to subtract them, then we'll get a vector which is close to the target vector T. So this is the idea which we're going to use in the reduction. So let me just describe the reduction. So in this one, we given a basis B and the target vector T. We generate the basis B prime, and we sample two short lattice vectors from lattice B prime, and make sure, and we terminate when we find two vectors whose difference is of form y plus t comma s, and this vector has a small LQ norm, then we terminate. Otherwise, we repeat this algorithm. So there are two non-trivial parts in this reduction. One is how to sample short lattice vectors by using SVP oracle. And the other one is how many times I have to repeat this reduction to get a vector which is of form y plus t comma s, and it also has a small LQ norm. So we'll talk about these 2 points in the next slide. So first is sampling the short lattice vectors by using SVP oracle. And this also comes from a already known technique of lattice sparsification, which is given by Subhash Khote. So in this one, we are given a prime P and a uniformly random vector Z. And if we consider the sublattice L prime Z, which contains all the lattice vectors V such that the dot product of Z with B inverse V is 0 mod P. And it's easy to see that L prime Z is also a lattice, and it's a sublattice of L. And due to this construction, it's easy to see that we get for a uniformly random Z, and for any vector V, the probability of a vector V to be in the sublattice L prime Z is almost 1 by P. And the idea for lattice sparsification is you choose a uniformly random vector Z, you generate the lattice L prime Z, and on L prime Z, you apply your SVP oracle and you will get a vector. And you repeat this algorithm many times. And if P is the number of vectors within a bounded length, then if you repeat it around order of P times, then you will get all the linearly independent, all the different vectors within a small bounded length. So this is the idea used by Noah Stephens-Davidowitz, and he showed that if we make polynomial number of calls to SVP2 oracle, then we can sample uniformly random lattice vectors within a sphere or within a L2 ball. And in this work, we kind of generalize this reduction to any LP norm, and show that similarly by making polynomial number of calls to SVP oracle, we can sample uniformly random lattice vectors in LP ball. So this is the solution of the first problem of how to sample small lattice vectors by using a SVP oracle. So the proof sketch here is, so first we show that there are two spheres S1 and S2, and the difference in their radius is not much, and also the number of vectors between S1 and S2 is not much. S2 has at most 2 to the epsilon m times the number of vectors in the sphere S1. So this is the first thing which we can show, and we can also put a bound on the radius of the sphere S2. And if we have a bound on the radius, we also have a bound on how many layers of the lattice L which we can have. And then we show that there exists a layer S in S1 which has all the lattice vector L, all the vector of form L plus k prime times the target vector T. And we can extend this set S to a set T, which is just a translation of a set S by a vector minus V plus T, which is also a lattice vector in L prime. And just by the difference in the radius of S1 and S2, we can show that this set T is in sphere S2. So if the number of layers in set S2 is not more than 2 to the epsilon m, then the number of vectors in set S is at least the number of vectors in set S2 divided by 2 to the power 2 epsilon m, and the same thing is known for set T. So if we do a uniform sampling over the set S2 or over the sphere S2, then with probability 2 to the power minus 2 epsilon m, we get a vector from set S, and with a similar probability, we get a vector from set T. And the idea is just repeat this, algorithm for 2 to the 4 epsilon m time, and you will get one vector from set S, you will get one vector from set T, and the difference of these two vectors is a solution to the closest vector problem. So this is the main idea of our reduction from CVP to SVP. So this is all. So with this, I conclude my talk. And in this work, we gave 2 to the epsilon m time reductions between lattice problems in different LP norms. And as a corollary of one of our result, we get a polynomial time reduction from square root m by log m approximation of CVP to SVP in L2 norm. So this is it. Thank you for listening, and any questions?
Are there any questions to Rajendra?
And if you want me to repeat any part, even that's fine.
Yeah, if not, yeah, let us thank Rajendra for the talk, and maybe we can disperse.
Thank you.
Yeah, thank you, Rajendra.